大家好，我是陈品瑜，我学号是11061216。
大家好，我叫陈信瑞，学号11060025。
And we are going to talk about the Basel problem in two ways. And it's first proven by Euler. And the first way I want to show is that I want to consider a spatial function. Well, just like integral 0 to power 2, natural log of 2 cosine x dx. This might be a little ugly, but you will see how I can do the magic, alright? Well, it's equal to, the cosine of x can be expressed as, e to the ix plus e to the negative ix over 2. So we can rewrite the formula and the real expression as e to the ix times 1 plus e to 2ix dx 0 to power 2. And because it's a product in the natural log, so we can separate it into two integrals, like e to the ix in the natural log, so we will have ix dx plus integral of natural log of 1 plus e to the 2ix, negative 2ix dx. And remember that I want to integrate the Taylor series of this part. So recall that natural log of 1 plus x is equal to x minus s cubed over 2 plus blah blah blah, and so on. So we will get 0 to power 2 ix dx plus integral of, e to the negative 2ix minus e to the negative 2ix times 2x over 2, and so on. The minus sign here. Sorry. And we integrate, we explain, and we do the integration here. So we will get, pi squared over 8i, minus 1 over 2i, and times, the boundary is 0 to power 2. So we will get e to the negative ix minus e to the negative 2i 2 pi, mistake here. Minus I pi here, alright? So 2 pi here. Mistake. Let me revise that. I pi minus e to the negative I, 2 pi plus e to the negative I 3 pi, and so on. And the denominator is 2 times the coefficient here, is also 2, and so on. So we will get 3 times 3, and minus, and so on. And this is the first term because we only plug in the power 2. So we need to minus when we plug in 0, so we will get 1 minus 1 over 2 times 2 plus 1 over 3 times 3, and so on. And notice that, well, this is kind of familiar, right? We know that e to the I pi is equal to -1 by Euler's formula. So we can replace it by this form. All right. We can do some more work here. We can multiply I on both sides, and we will get 1 over 2 plus 1 over 2 times. So here is -1 minus 1 over 2 square minus 1 over 3 square, and so on, and minus 1 over 2 square plus 1 over 3 square, and so on. And something interesting here has happened. Okay, alright. Some terms can be cancelled out by this minus sign. So we will get pi squared over 8i. So we will have what? Oh wait. We need to add I here. Minus, because we will add a minus here. Because we are going to do negative minus positive. And the scale is the same, so we will have a 2 over 2. And we will have the term that is not cancelled out is here is 1 plus 1 over 3 squared plus 1 over 5 squared, 1 plus 1 over 7 squared, and so on. Okay, and the most important here is that the function natural log of 2 cosine x is pluggable on the xy plane, and the boundary is just a real number 0 to power 2. So the imaginary part should not be there. So this should be 0. All right. So we will have pi squared over 8 is equal to this term. So we will have something like pi squared over 8 is equal to 1 plus 1 over 3 squared plus 1 over 5 squared, and so on. And this is beautiful but not the famous one. So we are going to find the famous one that is the thing that we want to prove. Is that 1 plus 1 over 2 squared plus 1 over 3 squared, and so on, just by the order of n. Just sigma 1 over n squared, n from 1 to infinity. And we are going to call it as an S. And we can manipulate the series a little bit to get another series. Just like we can divide 2 squared to the S is equal to 1 over 2 squared plus 1 over 4 squared plus 1 over 6 squared, and so on. And we found it is the missing part of this series So we can combine these together to get the x itself. So we will have s is equal to pi squared over 8 plus 1 over 4s, and we will have the s is equal to sigma 1 over n squared is equal to pi squared over 6, and that's down. Yeah, hooray.
Now we're going to prove the second. Now we're going to prove the same question in the second way, and this second way will be much easier and simpler because we learn almost all of the concept during the class. And this way is first developed by Euler, and then also the first time that human trying to fix this question. So we first know that sin x can be expressed as sigma n equal to 0 to infinity, or -1 to the power of n times x to the power of 2n plus 1 divided by 2n plus 1's factorial. And then we get these. And so on. Now we will divide all of them by x. So we got sin x over x. We get 1 minus x squared over 3 factorial, and so on. Now we want to extract this out, and we want its coefficient. And we know that this term, if we plug x equals to pi, we got 0. So we can develop sin x over x is equal to 1 plus x over pi, 1 minus x over pi, 1 minus 1 plus x over 2 pi, 1 minus x over 2 pi, and so on. Just as we said that we only want the x squared's coefficient, so we just find like these two, and we can get that negative 1 over 3's factorial will be equal to pi squared over 1, and plus, I think should add a negative over here, because like we all get negative. So we get like negative plus 2 pi squared over 1 plus 3 pi squared over 1, and so on. And this will equal to pi squared 1 over pi squared negative sigma n squared 1 over n squared. We take these two parts and we get 1 over 3's factorial will be equal to 1 over pi squared omega 1 over n squared. by moving this part over here, get pi squared over 3's factorial equal to pi squared over 6, and then we prove the function.